So as I stated in the last chapter, we're kind of going to skip around this chapter a bit and just really touch upon the important parts of it. We're not going to be doing everything in chapter 11, but I want to pick up where we left off and really go through a Taylor expansion of a function, because I think then you'll start to really understand what's happening here. And the function I want to start with is sine x. So we want to do a Taylor expansion of just sine x. So what does that mean? Well, sine x is not a very difficult function to work with, but as you learned all through Calc 1 and pre-calc and everything else, the easiest functions in the world to ever work with are polynomials. So if I can take sine x and rewrite at least part of it as a polynomial, well, different calculations, everything, some things start to become much easier. So to do this, you have to center it somewhere. So we're going to keep this one easy, and we're going to center it at x equaling 0. So what that means is my a is going to be 0. Sorry, not a equals a. Of course a equals a, but let's do a equals 0. So basically we're doing a Maclaurin series for sine x. Like, what is the Maclaurin polynomial that matches sine x? All right, so let's recall what our series looks like from 0 to infinity. It's f of n of a, and you put this little n in parentheses. That means derivative. So, f to the fourth derivative, fifth derivative, and so on like that, over n factorial. We're centering it at 0, so we can actually go ahead and replace. We know we're centering it at 0, so we can put it at 0, and we just have x to the n. All right, so expand that out a little bit so we know what it looks like. So let's just start with f of 0. I know I'm doing each little thing here, times x plus f double prime of 0 over 2 x squared. And I'm going to have you bring this out. Let's go to n equals 7, all right, for this particular one. You're going to see in a minute a lot of terms are going to cancel out, so we got to go kind of far out to really see what this looks like. So f to the third of 0 over 3 factorial. Okay, you get this idea. But if we want to go to the 7th, well, that means before you start trying to figure it all out, let's start a little chart of our sine function first. In other words, I find this kind of easier to do this. We know f of x itself equals sine x. And you can even go as far as saying, okay, so that means f of 0 equals sine 0. And what is sine of when x is 0? It's just 0. So if you want, you can kind of work all this part out first. So f prime, first derivative of x, is cosine x. Oh, wait. Cosine of 0 is 1. All right, so you get the idea. We're going to work out to help us do our coefficient. We can do this. That's going to be negative sine x. That's still 0. You'll start to see a pattern that falls. All right, the derivative of the second derivative, so the derivative of negative sine is negative cosine. Sorry, cosine. Negative 1. right? And then what's going to happen? It's probably going to start to repeat itself. So f to the fourth. I have no idea why I put a 3 there. That's an x of x. Is the derivative of negative cosine. Well, the derivative of cosine is negative sine, so negative negative goes back to positive sine x. Oh, well, you can see right away, right? Sine 0. And it's going to start to repeat itself, right? So I said I want to go to 7, so let's just write them out. This is going to be cosine. So 0, 1, 0, negative 1, 0, 1. And again, just write it out. You don't have to, but if it's the first time you're going through this, it might be helpful. And I said, let's go to 7. So let's do one more. So it's going to be negative cosine x, f to the 7th, 0 equals, that one's going to be negative 1. All right. So let's start. Sine x is going to equal, our f of x is sine x, and it's going to equal this Maclaurin series summation. So remember, it starts with f of 0. So you have this written down. So, oh, well, f of 0 is just sine of 0, so that's just 0, right? Plus f prime of 0. Well, we know that's 1 over 1 factorial. That's just going to be x. All right. Plus f double prime of 0. Well, if you think about it, that's just going to be 0. Well, the whole thing's going to go away to 0. In fact, anything that has the sine in it as its derivative is going to go away to 0. All right. So then I have plus f. So this was n equaling 0, n equaling 1, n equaling 2. So now I need n equaling 3. So I'm here. Well, that's negative cosine. That's negative 1 over 3 factorial x to the 3rd. All right. The next one's going to be 0 because it's going to be a sine. Now the 5th one, so this is n equaling 4 is another sine. The 5th one, well, that one's going to be cosine, which is 1 over 5 factorial x to the 5th. The 6th one has another 0. This is why I said we had to go to 7 because we needed to get some terms. And the 7th one, well, the 7th one is f to the 7th of 0. Well, that's negative 1 over 7 factorial x to the 7th. So let's clean this up and let's see what, don't forget dot, dot, dot. Yeah, it doesn't stop at 7. We're just stopping at 7 because we could literally go on forever. All right, so what does sine of x equal? Well, it equals x minus x cubed over 3 factorial. Do you see that? That's a 0 plus x to the 5th over 5 factorial minus x to the 7th over 7 factorial. You can guess, you can follow a pattern at this point, right? Plus x to the 9th over 9 factorial minus, so plus, minus, plus, minus, plus, minus. And notice it's only doing the odd ones. We'll talk about that in a little bit. And so on and so on and so on. Okay, this polynomial starts to represent your sine function. You can even write this polynomial. So this is the polynomial expansion for sine. You're like, well, how does a sine function look like a polynomial? We'll go to the graph in a minute. You've also worked with series now that you can literally come up with your own summation for this series. So 0 to infinity. All right, so what's happening here? Well, we definitely have an alternating series, right? So we have our -1 is alternating when n is 0, right? It's positive, and then so we're good. So we get to the n. And if you recall, so these are odd. How do we represent odd? Usually represent odd 2n plus 1 over same odd 2n plus 1 factorial. And try it, see if it works. Well, 0 is going to give me 0. It's going to give me x to the 0. It's going to give you 1. That's just all 1 x to the first, so that's just going to be x. When it's 1, I'm going to get -1, so it's negative 2, 1, that's 3, right? X cubed over 2 plus 1 is 3 factorial. See, it works. Yep. Just to show you, you don't necessarily have to do that, but it does work. All right. So this is important. This is something, oh, you'll pretty much need to memorize this if you need the sine of x expansion. So let's take a look at this on a graph because it's a bit cool. All right. So we'll start with just our sine x function. Let's get that graphed. And let's again, whoops, do that one in black so that one stays. All right. Now, I'm just going to use, you can do multiple graphs and it gets a little messy, but I'm going to put them all in one so that you start to see the function wrap around. Remember, this is centered at 0. So our sine of x started with x. Okay, well that makes sense. That's the tangent line at x equaling 0. Right? Minus, now I need x cubed divided by 3 factorial, and you can do that in Desmos. You would have to, you know, if you don't feel like working out your factorials, you can actually put 3 factorial. See, you can put 3 factorial, or you can put 3 times 2, which is 6. Whatever you want to do, doesn't matter. All right, look at that. Isn't that cool? As we add more functions, let me use a different color. The purple looks way too close to the black. Hold on. Let's use a brighter color like orange. Okay. And we're just going to keep adding. So plus x to the 5th. Whoops. Sorry about that. My thing got all screwed up. There we go. X to the 5th divided by 5 factorial. It should be 120. Look at that. It just started to loop a little further. So then I have minus x to the 7th divided by 7 factorial. Now, as you go further and further out, I mean, we can do more. We can do another one. Plus x, whoops, forgot the plus. Divided by 9 factorial. You get the idea. Okay. As it goes, as you keep adding more and more functions, of course, your expansion is going to just keep wrapping itself around the sine function. But centered at 0, you can see these two are identical within a certain interval. Okay, we're going to call that in our next videos. We're gonna look at that interval and call it like an interval of convergence, and we're going to see how big that interval is and everything. But for now, we can do the same with different functions. We can do it with our cosine. We can do it with our exponential. We can do it with e, and it allows us to use a polynomial for a certain point when figuring out sine, instead of using our sine function. So that's our Taylor expansion for sine. So what I want you to do right now, well, what do you know about sine and cosine functions? I want you to think for a minute about what you know about sine and cosine functions, right? You know, well, we know, think about that. What do you know? Well, you know, sine functions are odd functions and cosine functions are even functions. Take a guess as to what you think the cosine would look like, and then take a few minutes, pause the video, work it out a little bit just to confirm it, play with it on the graph, and come up with your cosine function, your cosine polynomial, your Taylor expansion, Maclaurin expansion for your cosine. Okay, so did you play around with your cosine? And hopefully you saw, bring this down a little bit. Sorry. With your cosine functions, your cosine's an even function, right? So if you work out, and I'll leave you to work it out, but if you work out your entire cosine function and you expand that using centered at 0 and everything else, well, now the 1 is going to remain. And instead of minus x cubed, you have minus x squared over 2 plus x to the 4th over 4 factorial. That's 2 factorial, which of course is 2. And then you have minus x to the 6th over 6 factorial. It's x to the 8th over 8 factorial. And so on and so on and so on. And that does make cosine an even function, where sine is an odd function. So now what I want you to do is take the time to come up with e to the x. So hit pause, go through everything we did with sine, and I want you to come up with your e to the x. Hopefully you were able to do that, but you can see real quick. So let's see. First function, of course, is just f to the 0. So that's just 1, because e to the 0 is 1. So let's just write that out. E to the 0, of course, is 1. What do we get for the first derivative? Well, the derivative of e to the x is e to the x. So you get e to the 0, because remember, we're going to, sorry, I didn't say that, but you're going to center at 0. We're just going to center at 0 for now. So this is the n equaling 1 is 1 factorial x to the 1 plus, oh, what's the next derivative is still e to the x. So this is when n equals 2, so you have 2 factorial x squared. Oh yeah, e to the 0, 3 factorial x cubed, and so on and so on. So e to the x is essentially is 1 plus x plus x squared over 2 factorial plus x cubed over 3 factorial plus x to the fourth over 4 factorial plus x to the fifth, right, over 5 factorial, dot, 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 dot. So what does that summation look like, right? It's the summation as n equaling 0 to infinity of just x to the n over n factorial. Look at that. If you don't believe it, go ahead and play with it on the graph. So that is your e to the x. So what does that mean? Well, okay. Suppose I didn't have a calculator that does, and I know this is a big stretch here, but you can imagine where there was a point in time where this was incredibly valuable. So suppose I wanted to calculate, suppose I wanted to calculate, oh, I don't know, e to the 0.3, 0.3. Well, if I couldn't just plug in e to the 0.3 into my calculator, I can use this series and I can say, well, that's going to be 1 plus 0.3 plus 0.3 squared over 2 plus, sorry, 0 plus 0.3 squared over 3. So we'll stop there. We're just, you have to stop it at some point, right? Can't go on to infinity. So what does that give me? That gives me 1.03 plus 0.09 squared plus 0.027. Factorial, right? I forgot my factorial. Sorry about that. So that's actually 6. So yeah, you'd have to do a little division. All right, and that's going to be about 1.03 plus 0.045 plus, that comes out to about 0.0045. There we go. Then I get 1.3495. Okay. Well, if I plug it into my calculator, which you can do, e to the 0.3 is 1.3. So what do I, 1, 2, 3, 4. So let's bring it 5 decimal places in the calculator. 1.34986. This was 1.3495. Okay. Clearly, if I continued adding terms, I would get closer and closer to I would then get 986, and I could get closer and closer to the actual calculated value. Well, I can calculate the error here because I put it in a calculator to see what it is. You get an error anytime you use an estimate for something. So we're using a polynomial estimate. We only went to n equal 4. I mean, your error would be less if you went further. Is obviously, because I was able to calculate it, I can just take 0.34986 minus 1.3495, and I can get that 0.00036. But that's not a really good way to estimate your error because you'd have to actually calculate the actual value. So how can we estimate our error without calculating the actual value? So here's a theorem that states that your error is approximately equal to f n plus 1 of a over n plus 1 factorial x minus a to the n plus 1. Well, what do we mean by n plus 1? So if n is used in your estimate. So for our example, we used n equaling 4. Do you see that? That's n equals 1, n equals 2, n equals 3, n equals 4. So if I want to estimate the error, what I have to simply do is the next calculation, or use what we call the first term you don't use. Okay? So if I'm estimating using n equals 4, I need to actually calculate n equals 5 to get an estimate of my error. Now again, we calculated the actual error just by plugging it into a calculator. We don't want to plug into a calculator. So we want to get an estimate of the error. We just use the next term. So what would n equaling 5 be? Well, that would be, so take a look for a second. Notice at n equaling 4, we're on the 3 factorial, right? That was cubed. I don't know. Sorry. I see I put a squared there. Sorry about that. That is cubed. N equaling 2, we're on 2 factorial. So to do n equaling 5, we're actually looking at 0.3 to the 4th over 4 factorial. Which is approximately 0.0003, I think it's 3375. Again, this is just an estimate of our error. We stated, because we put it into a calculator, is 0.00036. We're at 0.00034. So we're close. It's, again, just an estimate of your error. You can get that estimate by calculating the next term. All right, because basically it states your error, your actual error, is going to be close to the value of the next term. Okay? Granted, your estimated error is going to be a little lower because there's more terms to add, but those terms start to get really small, so it doesn't matter. So let's do one more example. Let's take a look at, let's estimate ln of 1.04 using, let's just use 3 terms, n equals 3. Okay, so to do that, so since we're over, so this is an interesting one because you can do, if you look at the notes that are posted in Canvas, you can, or you can work it out on your own. You can do an expansion of ln of x plus 1. It's a pretty common expansion. It ends up being x minus x squared over 2 plus x cubed over 3 minus x to the 4th over 4, dot, dot, dot. All right, so that's your expansion of ln of x plus 1. And again, there's a lot of common expansions like sine x, cosine x, e to the x that you're just going to need to get familiar with. And this is one of them. And if not, take the time, write it out, and you figure out your expansion of ln of x plus 1. Now, why is that helpful in this problem? Because you can let x be 0.04, right? Because by letting x be 0.04, then we are expanding 1.04 with x equaling 0.04. All right, so that gives me 0.04 minus 0.04 squared over 2 plus 0.04 cubed over 3 factorial, over 3. Sorry, they're not factorial. And that's approximately 0.03922213. So then to get to error, the approximate error, we would just take the next term, 04 to the 4th over 4. That's going to give me about 0.00000. I think that's 6. 1, 2, 3, 4, 5, 6. 6, 4. Okay, but that's good for now. In the next set of videos, we'll take a look at expanding. We just wanted to, in this video, I took you through kind of looking at the Taylor expansion of sine of e to the x and of cosine, and also looking at error just a little bit. So we'll get into more expansions. We should do some examples of expanding away from 0. And then when there's a lot of properties and the idea of convergence and coming up with intervals of convergence, that we'll look at in our next set of videos.